important application of Laplace. We go ahead with the application of Laplace transforms. For that, we need all these Laplace transform of derivatives. Instead of ft, I just prefer to write it as a y dash t. In ordinary differential, we'll be discussing dy by dx terms of that kind. So we just replace your small f as small y, and fs I'll write just as fs is Laplace of f of t. So I'll write Laplace of y of t. I should have written Laplace of y of I should have written Laplace of y bracket t, but I'll simply write Laplace of y just for a easy way of writing. Okay. So this application needs both the concepts Laplace and its inverse, because we'll be writing the Laplace of a given equation and then finally write the inverse to get our solution. So basically the Laplace converts your differential problem into solving an algebraic equation problem. Solving algebraic equation is quite simpler than solving differential. So that is the main purpose and application of Laplace. Here we have discussed on ordinary differential case, and you can refer to further partial differential cases in later sessions, later classes, courses. Fine. Okay. Now we have this question: solve a second order differential equation. We have a lot of methods. Homogeneous equations have non-homogeneous. Everything have some methods to write, but you can discuss. There are some differential equations where this finding the roots, getting the complementary, particularly it's going to be a big, huge process. So any such discussions of Laplace, we can just try out finding the solution by Laplace transform. We should have some initial conditions at zero value of your function and its derivative. So I have just returned the question here again in a simpler form: y double dash 2y dash plus y. And now this is the first step where I have taken the Laplace on both sides. So this is equation, I have taken Laplace on both sides. By linearity I can split and write. Here comes our formula. The formula what we wrote here. We need to convert all these derivatives into Ly function. So that is what done here. So this is going to be, this is going to be this. This L of y double dash. This is L of y dash. You can use these initial condition values to substitute for these y0 and y dash 0. Then you pull out common terms of Ly, and the other things you can take it to the right hand side, and we end up in this Laplace function. So where is our solution? We have just given an equation. We have found the Laplace of the variable y. My solution will be y. I should get y. Only then I reach my solution. Okay, here comes the inverse part. Okay, how to get y? Now that I have L of y, I have to get y. Take inverse on both sides. When I take inverse on both sides, it's going to be of this kind. So at this stage, we'll have to have good knowledge how to find the inverse with various discussions, whatever we have dealt, or properties. So take this as your capital Fs function, and we observe this is s plus 1, this is s plus 2, and this is a s square plus 2s plus 1 or s plus 1 whole square. So you can club and write it in this form, isn't it? Now you adjust the numerator to be s plus 1 form. So I just write it as s plus 1 plus 1 and apply the shifting theorem. I can write it as in inverse. After writing the inverse, I can apply shifting and write it as s plus 1. So this, observe, this s plus 1 has become s and this s plus 1 has also become s. And now go ahead splitting the denominator, get your solution. So this differential equation is solved by using Laplace, first by taking Laplace transform and then by taking inverse Laplace transform. So this is for your second discussion. Same way, I have a function, I rewrite in a better format, take a Laplace on both sides, apply the derivative formulas, again get your Ly. This is my Ly function. Go ahead finding the inverse, but when you go for the inverse, it is cannot be clubbed as single factor. You have three different factors and this is a quadratic, so I have to go by this split up of terms, and then you get your ABC values by partial fraction method. This comparing is better than substituting some arbitrary values, so do compare and highest coefficient to get the remaining constants. After getting the constants, this is how you will end up in. After getting this, you just observe the first term is just minus 1 by 40 is a constant. 1 by s plus 3 I can write the Laplace. This also I can write the Laplace. Coming to this part, you can have to split into two terms, the common denominator, and then you can write the Laplace, which is your final solution. Okay, the same way we have another problem. Please go through this. And it's worked in a similar way, but here you have 5 constants because you have to write s square minus 1 as s plus 1 s minus 1 and s cube as s square s cube. So you will be dealing with 5 constants, but all are simple, so you can just do some comparing work and get the constant values. But finding inverse is very simple, nothing much complicated. And you also observe here the variable is given as a x variable instead of t. So I have just used here, wherever I apply inverse, I have used a x variable and not a t variable. So again it's a similar kind of problem. So please go through this, but this requires some shifting property because there is some manipulative work to be done. And here I end up the Laplace discussions with an application to ordinary differential equation solving. There are problems where we can solve the simultaneous differential and partial differential, which will be dealt in further courses. Thank you.